Today I'm going to be talking about my project that I have been working on with other people. Like she said, I'm from chemistry, so today I'm going to be talking some chemistry, so just bear with me. I hope I make it easy for you to understand. Before I dive in details and talk about my project, what I've been doing, I'd like first to start talking about a very important motif that exists in many drugs. So this motif for today is dye-substituted motif. There are two examples of this motif. The one is called the 4,4-diarylpiperidine motif, and the other one is 1,1-diarylcyclohexane motif. 4,4-diarylpiperidine motif exists in many drugs. Some examples of these drugs are that budipine is known to prevent seizure or control seizure. The other one is niglidipine. It's a calcium channel blocker to treat the high blood pressure. On the other hand, the 1,1-diarylcyclohexane motif exists also in different drugs. I picked two here to show you. So the two drugs for today is the AC-131 and 186. Those are known to treat the neuropathic pain. So due to the biological activity of this motif, many people have been interested in making it. So one way to make this is through Friedel-Crafts reaction. So this is in 2019, Ball found that if you start with the phenylpiperidine alcohol and you react it with electron-rich nucleophile like dimethoxy, and in the presence of a stoichiometric amount of very strong Lewis acid, this leads to the formation of the FC product, which has the 4,4-diarylpiperidine motif. Other example is McMillan in 2010. The same thing, he found if you start with a phenylcyclohexane alcohol and you react it with electron-rich nucleophile in the presence of electron-deficient bronze acid, this leads to the formation of the 1,1-diarylcyclohexane motif. Let me walk you through the mechanism of this reaction, talk more in details. So the first step, again, you start with the alcohol. You react it with the electron-deficient Lewis acid. When you do that, the Lewis acid is going to bind to the hydroxy group. So when it binds to the hydroxy group, it helps to polarize this carbon-oxygen bond, makes it easy to break. So basically, this trichloroiron will pull the electron density from the carbon-oxygen, makes it easy to break. But in this hand here, the carbon-oxygen is not easy to break. So you do need Lewis acid to do this step. Once the carbon-oxygen bond breaks, this leads to the formation of the carbenium species. So one thing here to point out that's interesting is the fact that you need very strong acid to help form this carbenium species. This has caused the function group tolerance to be limited. So one way to expand the function group tolerance, because if you try to do this reaction, having electron sensitive function group, this reaction is going to fail because the strong acid is going to cause the sensitive function group to decompose. So one way to avoid this and generate the carbenium ion is using weak acid. Using weak acid helps to expand the scope of function group tolerance. So once you form the carbenium ion species, this has two routes to go. Route number one is to get intercepted by the electron-rich nucleophile, like in this case the dimethoxy, to lead to our desired product. But another route that can take place, which you cannot prevent, is this proton to get eliminated to form the phenylpiperidine alkene. This product is dead end, and the fact that you cannot control these two routes because both of them are happening at the same time, this caused the reaction yield to be low. So if we could somehow prevent this route from taking place, this would cause us to increase the yield of this reaction. And this is what we have been doing in the lab, is to find weak acid to generate the carbenium species and prevent this routes to increase the yield. Before I talk about that, I want to talk about our group, what we have been doing in our group. Our group is interested in cycloalkene because in the presence of photocatalyst and blue light, this cycloalkene can go under photoisomerization from cis to form the strained trans cycloalkene. This right here, the starting material is stable, but this one is less stable. So going from more stable to less stable, you do need a catalyst. This is an endergonic process. Basically, what happens is the photocatalyst get excited or absorb the blue light photons. It transfers this energy to cycloalkene. This cycloalkene absorbs the photo energy and transfer it to strain energy. We call this cycloalkene as a transducer because they convert the energy from one form to another form. So we have been exploiting this strain energy to drive different reactions. One of the reactions we did is we showed that we can do intermolecular nucleophilic substitution with this transphenylcyclohexene. So when you react it with alcohol, this leads to ether formation, and when you react it with secondary amine and CO2, this leads to the formation of urethane. Another reaction we showed that we can do ring opening. We can open this transphenylcyclohexene to get to this product. And all of those are very important products. I don't have time to go in details like what they can do, but I'm just gonna show the product. Another reaction, we can do cycloaddition reaction. Basically, the phenylcyclohexene can react or transphenylcycloheptene can react with this cis-phenylcycloheptene to lead to this cycloaddict product. This is another type of cycloadditions. I'd like to walk you through details of this step more to show you what actually is happening. So if we look here, you have the ground state cis-phenylcyclohexene, and in the presence of photocatalyst and the blue light, the photocatalyst is going to absorb the blue light photons. It's going to get excited. Then this photocatalyst, the excited photocatalyst has the ability to transfer the energy to cis-phenylcyclohexene. Luckily, this cis-phenylcyclohexene cannot take this energy and absorb it. Then when absorbed, it gets excited to the triplet excited state, which will look like a planar biradical. As you see, when the cis-phenylcyclohexene got excited, the double bond right here got broken. And the fact that it got broken, sigma bond can rotate, but double bond cannot rotate. The fact is this sigma bond can rotate, it helps to minimize the interaction between these two electrons. This leads us to the formation of this species perpendicular biradical, and this perpendicular biradical has two radics to go to. Either relax back to cis-phenylcyclohexene, and if it does that, that's fine because this step can keep happening over and over. Or it can relax to form the transphenylcyclohexene. That's what we're interested in. This transphenylcyclohexene, due to the strain energy, can act as a base. What I mean by that, it can grab a proton. But I'd like to show different transphenylcyclohexene or different cycloalkene that we worked with. First of all, let's start with the phenylcycloheptene. This one cannot form the trans because the ring size is very small and the strain energy is too high. It will stop at this step right here. It can't go to this other step. But again, the phenylcyclohexene can form the trans, and this is what it looks like. And this benzene cyclohexene cannot form the trans because of the outer ring. Again, it'll stop at the biradical species, and this is the other ones, they can form a trans. So people calculated the strain energy, how much is strain energy inside this molecule. So for a transphenylcyclohexene, the strain energy is 53, and for cycloheptene 36, and for benzocyclo BC7 it's 43. So the thing is here, someone might ask why the strain energy of this one is higher than phenylcycloheptene. Well, the reason is for that is the ring size. This ring size, so the smaller the ring, the more strain energy. The stronger acts as a base. But the larger the ring, the less strain energy that ring has. And is not going to be as a strong base as the trans-phenylcyclohexene. There are different reactions they can do, but today I'm going to be mainly focusing on phenylcyclohexene. My time is up. Sorry. So it can get proteinated. So the question is, what different acid can we use to proteinate it? There are different varieties of acid that we can use to proteinate this trans-phenylcyclohexene, starting from the weak one on the right side and the strong one on the left side. Again, as I mentioned before, we want to avoid using a strong acid because we're trying to expand the functional group tolerance of the Friedel-Crafts reaction that I'm going to show you. So we found that we can use weak acids. This is some example. The problem, so when we screen different acids, we find that pyridine base works the best. Someone might say, okay, why didn't you use water? The thing is, when water protonates the trans-phenylcyclohexene, you generate the carbenium ion, but the conjugate base, the hydroxy ion, it reacts with the carbenium ion. We don't want that. We want the electron-rich nucleophile to react with the carbenium ion. We don't want the conjugate base to react. So since we're going to be using the pyridine acids, and they are known to be weak acid, they need the counter ions to stabilize this proton. So, but one of the hardest things is to find the nanonucleophilic counter ion. The reason for that, again, when you use pyridine salts, you're gonna protonate, you release the X minus. This is the counter ion I'm talking about. We don't want this to react with the carbenium ion. We wanted the blue nucleophile to react with the carbenium ion to lead to our desired product. So with this in mind, we screen different counter ions. We screened the chlorine, triflate, and tetrafluoroborate, and hexafluorophosphine. We found the hexafluorophosphine works the best and gave us higher yield, and the reaction was faster. The chlorine caused the reaction to be slow and gave us a very low yield. The reason for that, after the collagenium proteinate, the chlorine minus ion will add to the carbenium ion. This entire step right here gets shut down. So I'd like to talk about different substituents that we studied. We studied different substituents in the outer ring of phenylcyclohexene to see how they impact the yield. So first we start with electron with the hydronic group, and they gave us a good yield. But when we had two electrons with the hydronic group in the phenylcyclohexene, the reaction did not work. We think the reason for that is this carbenium ion species that we need to form this so this can get intercepted with the electron-rich nucleophile. But we don't think we're forming this. This is very less stable. The reason for that, because you have two electrons with the hydronic group, they pull the electron density away from the carbenium ion, which is known to be electron deficient anyway. So having two electrons with the hydronic group makes it even more electron deficient. And also other substituent we screened is the electron-rich one, and they also give us a good deal. The second thing we moved to screen is different nucleophile. We find out that 5-membered aromatic nucleophile works good. In the case of pyrrole, we got two radioisomers, as you see, where it's attached to carbon 3 here, and here pyrrole FC product is attached to carbon 2. 2-methylfuran worked, and here thiophene, 2-methylthiophene, worked, and here thiophene, which we found that 2-phenylcyclohexene adds to it. Because this carbon and this carbon, both of them are nucleophilic. You cannot control phenylcyclohexene to add to just one carbon. Another thing is, so these are known to be electron-rich nucleophile. We were interested, can we use electron-poor nucleophile? Like for example, the case pyridine. When we did that, we found out that pyridine can intercept the carbenium ion. So we did not form this product. But we find another way to get to this product that we want, because the straight pathway did not work for us. So what we did is, since we know that we can form this pyrrole FC product, we did ring expansion. We expanded this ring by one carbon to get to the desired product. Here other also nucleophile that was screened. Here we showed that we can use acyclic alkene, so you don't have to use arrow nucleophile. You can use acyclic alkene because also they're known to act as a nucleophile. Other thing, Other nucleophile we screened is the aryl hydroxy. The reason for that, because we wanted to see if we form the carbon-carbon FC product or the carbon-oxygen product. The aryl hydroxy are known to have two nucleophilic sites, the oxygen and the carbon. So we just want to know which one of those can we form. The mechanism for this, again, you have phenylcyclohexene in presence of photocatalyst and light. It goes under photoisomerization. You form the trans. Then this gets protonated. You form the carbenium ion. Then you have this aryl hydroxy. The oxygen here is more nucleophilic, so this route will lead to the ether. This route will not take place because the carbon here is not that nucleophilic. But we find out, okay, that's fine. We can, if we form the ether, we can heat this ether and reverse it back to the CC. Okay, sorry. FC product. So this is some of the product we made, and here's literature suggests that if we use the phenol FC product, we can get to the drug that I was talking about in the earlier slide. This is different substituent is we screen in the phenylcyclohexene, the aliphatic ring of phenylcyclohexene. So here I'm showing that if you have methane in position 4, you get 2 product. Here, if you have 2 methane in position 3 and 5, you get only 1 product. You can have carbonene, and this pyridine one also works with us. Lastly, this is the last thing. The mechanism again, one more time, is phenylcyclohexene again absorb the photo energy from the excited photocatalyst to form a trans-phenylcyclohexene. This can get protonated by a weak base. That's what exactly what we wanted to do, to expand the function group tolerance to form the carbenium ion, because people in the past that were using very strong acid to form the carbenium ion species. Then this can get intercepted by electron-rich nucleophile to lead to desired product, or can get eliminated. But if it gets eliminated, you form the phenylcyclohexene in your starting material. That's fine, because in ball chemistry, when this gets eliminated, you form the phenylpiperidine alkene. This is dead in the product, but in our case, we can keep reusing it over and over and over. So this is some of the improvement we did. We used photocatalysts. We were able to use weak acid and increase the function group tolerance. Also, we were able to generate carbenium ion dynamically, as opposite of those people, they will not generate the carbenium ion dynamically. And this has caused us to increase the yield of this reaction. At the end, I'd like to thank my supervisor and my group members, and this is a picture of our group, and I'd like also to thank the funding agency. So, thank you. I'm sorry for taking too long. There's a lot of detail.